Ok, boa tarde a todos. Good afternoon, everyone. Thank you for joining us into another seminar of the Astronomy Department seminars. Today, I'm very pleased to present Professor Martin Pohl from Potsdam University and from DESY. I will very briefly introduce Martin. He is a lead scientist at DESY in the field of astroparticle physics and professor for theoretical physics at the University of Potsdam in Germany. And together with his team, he studies energetic particles in the universe, their sources, their interactions with their environment, and their decay products. So, Martin?
Thank you, Maria. So while we prepared for the presentation, the projector was acting up a little bit, and one may be inclined to throw the remote control for the projector against the wall. I will not do this. But if you did, you would notice that the projector might have about a joule or so in kinetic energy. And exactly the same energy you may find carried by some single atomic nuclei in the universe. And therefore, you have extremely energetic particles. We call them cosmic rays. They're charged, and here you see the energy spectrum begins somewhere at a TeV or so, goes all the way to beyond this joule. And if you look at them, of course, this continues at lower energies, but if you look at them, you notice that the energy density you have is very similar to that of magnetic field, is very similar to that of radiation, at least in normal galactic environments, and is very similar to the thermal energy content of interstellar gas. And then obviously, these cosmic rays have a huge impact on a variety of processes in the galaxies, from star formation to the structure of galaxies as a whole. So they're very interesting. They're very sort of unequally distributed. And the real question you may ask is, how does nature do this? How does nature give particles so much energy? And just for scale, I'm comparing here, in the sense of center of momentum energy, cosmic rays on a stationary target like the Earth atmosphere or interstellar gas. You have the same center of momentum energy as for collisions at the LHC here, roughly. But the spectrum continues for another 3 or 4 orders of magnitude, which, by the way, is a problem because we don't really know the particle physics here. But this is extremely much. So basically, nature is a better engineer than we are. And well, how does this work? So the first thing we need to realize is that in space, charged particles interact not by collisions, they interact by collective electromagnetic fields. Magnetic fields you have pretty much everywhere, but electric fields you do not. Essentially because the conductivity is extremely high, and that kind of kills large-scale electric fields. And if you then look at a charged particle in only magnetic field, you know what it does, right? So it's basically undergraduate physics. So what happens if you have a homogeneous magnetic field indicated by that blue arrow here? Your particle will spiral around and spiral and spiral and spiral. Nothing happens. If you put in a perturbation into the magnetic field, then essentially you change the pitch of the spiral. But it will continue to spiral at the same energy because interactions with the magnetic field don't change the energy. So you need something else. So first of all, these fluctuations in the magnetic field have a huge impact on the spatial propagation of the particles. So they're really important for that. It's not to be forgotten, but for energy gain, you need electric fields. And you need electric field that you cannot let go away by transforming to some other frame of reference. So how can we understand this? How can we understand the magnetic field fluctuations? So a natural way of doing this is to think, well, we have very low frequency waves, electromagnetic waves, and there's a whole zoo of wave types, Alfvén waves, Whistler waves, and whatnot waves. So you can think of a superposition of these waves. Now the thing is, in particular with electromagnetic waves, you always think they have an electric component. Well, if you're in the rest frame of the wave, they don't. And so if all the waves had the same rest frame, then in that particular frame of reference, there's no electric field. You can't change the energy of a particle. So what you need is essentially different rest frames of different parts of the fluctuating electromagnetic fields. Because then whatever Lorentz transformation you do, it doesn't help. There will always be electric field that's left over. Okay, so this is the situation you need. So how do I know which kind of field or which type of wave a particle would respond to? Well, waves are described by a wave factor that kind of looks like this, a complex exponential. There's the wave factor, the spatial coordinate, and there's the frequency in time. What's relevant for the particle is the state of the wave at the location of the particle, and the particle itself moves. So basically for this x, you have to put in the trajectory of a particle. Maybe it moves in the same direction as the wave vector of the wave. Then basically you have its velocity times time. You already noticed that, okay, so basically then there is time in both of them. I can factor this out and have something times time. If you work out, for example, the V cross B force, V is essentially given by the forward moving part of the velocity along the magnetic field line and then the oscillatory part with the gyration frequency. You get the same thing plus another time-dependent term here that involves the gyration frequency. But whichever case it is, right, you end up with an expression that is time times something which is the sum or difference of certain quantities. Now, if the sum or difference is a large number, then you still have very rapidly oscillating fields at the location of the particle, therefore it will jitter a bit, but not do much. If, on the other hand, that sum or difference is essentially zero, then you have the wave at a standstill and V cross B is a constant. That changes the state of the particle a lot. And in that case, would give scattering. Right, and for 50 years, maybe 60, we thought that this is basically all that's to it. And now we know a bit better. Now we know that on top of these resonant interactions, so the particle picks a specific wave, we also have non-resonant interactions. There may be mirroring, particles may be trapped, and a number of things happen on top. So this entire business is far more complicated than that, and I'm actually here to work with Beta on these topics. Okay, but it's important to understand that we basically need an understanding of the electromagnetic fluctuations or turbulence to understand what's going on with my particles. Now let's see how we can use that to understand how particle acceleration work, and also at which cosmic object we can study it best. Because you always need to use observations to understand what's going on. And what I find most interesting is the remnant of a supernova explosion. So here we have an example. It's one of these nice false color images. So not the image is false, but the color. And different colors essentially here refer to different energy bands of X-rays. And then partially this is just thermal stuff, basically line emission of iron, silicon, and whatnot. Partially this is actually synchrotron radiation. Now the nice thing about these things is A, they are non-relativistic outflows. So I don't have to worry about specifics of the geometry too much. But nevertheless, I can resolve the object, obviously. They're also persistent. They evolve very slowly. And that means you can collect all kinds of measurements you have in the radio band, in the X-rays, gamma rays or so, that have been taken over the years, and you can combine them. That's not the case if you have an explosive event like a gamma ray burst. These things are really good. But not easy, though. One of the things that's difficult is the following. On the left, again, you have one of these false color images of this time a different supernova remnant. Again, it's resolved, and just to give you an idea of the size scale, this white bar is about a light year. Okay, so it's a couple of light years in size. Now you see that what's depicted here in blue, again, that synchrotron radiation, that starts here, at a very sharp boundary, which is actually an outer shock front. And to understand these shock fronts, where we think, quite a bit of the energetic particles are actually produced, you have to look at the right animation here, where we actually look at a kinetic simulation of such a shock front. And what I'm showing here in particular is electron density. So red is high, blue is low. This is one component of electric field, actually the one along this line. And here the color is sign preserving, or anything dark red or dark blue is actually large amplitude. Same thing here, one component of the magnetic field. And you're looking at the shock transition. First thing you see is what you read in the textbook about shocks. It's not really correct. These things have a certain thickness. The second thing you notice is, so this is huffing and puffing and so forth quite a bit. And that's basically due to all these waves that are produced and that mediate the transition at the shock. So you see here, you see a couple of electrostatic ones. These are very low frequency electromagnetic waves and so forth. They're partially compressive, so you see very high density. Here in the shock transition, much more than the normal hydrodynamic or MHD jump conditions would indicate. Now the real trouble is this white bar there, because that's about a light millisecond for a typical supernova remnant in the galaxy. Which means this thing is about 10 to 11 orders of magnitude larger than that thing. This one I need to understand to figure out how these cosmic rays are produced there, at least the low energy ones. But the thing on the left I need to understand to model the entire radiation we observe from this thing. And there's no single tool that works over this extremely wide range of scales. And that's one of the really huge problems we have. So the simulation technique here on the right covers only very small volumes in very short periods of time, for example. Okay. So do we have an idea how particles get accelerated? Yes, we do. And it's depicted here on the right in a very simplified way. Again, this is supposed to indicate one of these shock fronts, where, in a nutshell, stuff comes in from the left at high speed, gets compressed, and it vects further to the right at lower speed on the other side. Okay? Now, why is this interesting? It's interesting because if you have electromagnetic waves that fluctuate a little bit and may have some electric fields, on the left half of the panel, you have a chance to look at that in a frame in which the electric field is very small or disappears. You can do the same thing on the right, but you will notice that the two frames are different. And so globally, there is not a single frame of reference in which the electric field disappears. Great, because we need an electric field to accelerate particles. You can look at this in a slightly different way, as that this is a compression system. Basically, you get adiabatic heating or a heat pump. if you so want. You can describe this, and it's to a degree scale invariant, except that you need to feed in particles at low energies, for which we need something like the simulations I showed on the previous slide, and you need a little bit more. So your particles are supposed to move about, cross the shock front a couple of times, get scattered, changes in direction on either side. And this is where the problem arises, because you need something to scatter them. You need those fluctuating magnetic fields, and the more you have of that, the more rapidly you can scatter, the faster you can energize your particles. And you need to have this here on what we call the upstream side, where pristine material comes in. So that stuff doesn't yet know about the shock, right? So, but what does have a chance to get in there are again your cosmic rays or energetic particles. Essentially, if you model this, you find that in the shock rest frame, the cosmic rays on the upstream side have a vanishing bulk speed. The cold plasma, on the other hand, has not. So these two stream relative to each other. And that's fertile ground for the growth of all kinds of plasma waves. And the idea is that this way you drive plasma waves that then provide the scattering and sort of make this process continue. Okay. This all sounds, pretty okay. And no obvious showstoppers here. But if you think a little bit further, you notice that, wait, so this picture involves a normal shock transition, right? Normal shock transition is meant to preserve mass flux, momentum flux, and energy flux across the shock. Okay, but we always use sort of the gas or the cool plasma for that. But if you accelerate very efficiently, and I said before something about the energy densities of cosmic rays, then maybe we need to also account for the momentum flux and energy flux of those cosmic rays. So wouldn't that modify my shock? Well, yes. And if you work this out, you notice that they would modify the shock to make it at least partially far more extended. And the end result is that low energy cosmic rays then overall see a different compression than high energy cosmic rays. And this translates in the scale invariant picture into a different spectrum or different power law or a different index at low energies and at high energies. And some 20 years ago, we thought that, yeah, this has to happen. This is unavoidable and will be there. So here on the left, you see this is taken out of a paper, and I will not name the author, right, because this is not what we see. So you get various spectra here shown. There's a number attached to them, and that number essentially describes how efficiently particles are pulled out of the thermal pool at the shock and then made accessible to the shock acceleration process. So, very small values, maybe this looks like a straight line or a power law, but as soon as you make this larger, you see that there is considerable curvature. Okay? Good. Now, what this means is that the high energy particles here, somewhere in the TV band, they should all have relatively hard spectra. And when you then work out what you expect to see in gamma rays from these objects, maybe it's something like this red line here. So just for scale, this is a GeV, this is a TeV. Okay? And the representation here directly corresponds to that. Now, I'm also showing GeV band gamma ray data and TeV band gamma ray data. And I mean, we don't need to go into the details of that modeling to see that the red line doesn't really fit. Okay? And that's not the only example, it's basically all of them. We simply don't see this very strong cosmic ray induced modifications of shocks and the acceleration process. Okay, but we do see something else, which may or may not be related. So here I show from the same object two different figures. The one on the right, I believe, is older, so I show this first. You see a couple of data. This is energy flux per logarithmic energy band. You see that's basically synchrotron emission in the radio. There's this X-ray synchrotron, and there's this something in the TV band. Now this is all synchrotron, and here we basically have two options. Either you have ions that undergo collisions, produce pions, and so forth, and then part of those will decay into gamma rays, and that will give you something like this reddish dashed line here. Or you take the same electrons that you see through the synchrotron radiation and consider them Comptonizing the microwave background and whatever other radiation field is there. That gives you the cyan line here. Do I have complete liberty in sort of choosing the relative amplitudes? No. What the ratio is between the peak of this Compton emission and the peak of the synchrotron emission is fully determined by the magnetic field strength, the average field strength in the emission zone. Do I make this small? Then, maybe this Compton component basically already walks through my data points and I cannot afford more. Therefore, in this case, I get a lower limit for the magnetic field strength. That's ballpark 80 microgauss. And if you think this is what we call a type 1a supernova remnant, these things sit in no man's land, where the magnetic field is 5 or 10 microgauss. You compress this at the shock, then maybe you have 20, but you're not going to get 80. And so there must be processes that amplify the magnetic field. Okay? And if you want to allow for a bit of this hadronic component through the pions, then you need to make that Compton component weaker, and the way to go is further increase the magnetic field strength, which makes the need for magnetic field amplification even stronger. And then on the left, this is all the same thing later. So now in the TV band, we have a couple more data points. And we also have some in the GeV band. Again, this kind of pion decay curve, blue, Compton curve, this greenish one. Red is the total. And you actually arrive at somewhat larger requirements. So what does happen, apparently, is that the magnetic field is amplified, but the cosmic rays are not so many that they very substantially modify the system, which is a bit counterintuitive. Okay, good. So now let's look a little bit into how we model these things. Yes? Yeah? Right.
But what about having both?
Well, this is what you have on the left, where you argue that the GeV part comes from the pions, the hadronic component, but in the TV, well, what is this, a 70-30 share or something in favor of the Compton component?
Or the other way around?
Well, the Compton component is typically very hard, so if it dominates anywhere, then it's in the TV band. It's very hard to get it terribly strong at GeV energies. Yeah, I mean, this is for supernova remnant. I mean, if you go for another system, different parameters, all bets are off, right? But you can go through the same logic. Yeah? Good. All right, so let's model this in a bit more detail. So we've seen that we have this electromagnetic turbulence that scatters particles around, which means it will try to hold on to your cosmic rays, but they have a bit of liberty, and this typically ends up in some kind of diffusive motion. But it's diffusive motion relative to the rest frame of that turbulence. So if that moves, for example, because the entire plasma moves, then there is also an advective component of spatial transport. Okay? The rate of acceleration, I already mentioned, this depends on the turbulence spectrum. Why? Because the rate of acceleration depends on how quickly you can make these shock crossings and return again and return again. So how quickly you basically bend the trajectories. That depends on how much turbulence you have, and then possibly also turbulence at the right wave number, hence the spectrum. So this shock modification is not observed. We all reset that. The shock structure in itself, what I showed in this little animation before, is really relevant for pulling particles out of the thermal pool. And I'm not going to talk about this because this is a seminar talk in itself. Okay? Good. So what you can do is you can write down a continuity equation for this. Of course, you will want to make it time dependent, and then you have the divergence of the flux. There's diffusive flux, advective flux. Yeah, okay, good, we expect this. What the particles may do, in particular the electrons, will radiate very efficiently. That's an energy loss process. Maybe you want to account for this. This is the flux in energy space. There is our adiabatic compression or expansion term that has to be there. And there is a source term that basically describes this pulling of particles out of the thermal pool at the shock. So this guy's non-zero only at the shock, and this only gives you something at very low energies. It's this one that provides the acceleration up to extremely high energies. Now, what you need to know, right, so, well, you need to know the flow speed basically here and there. So that means the first thing you have to do is you look at the supernova remnant and basically look at the flow profile of it. So do hydrodynamics or MHD, put something on the large scales, right? And then you can, at each location, put in the appropriate velocity here. If you want to model the shock acceleration, or if you want to know where you want to pull particles out of the thermal pool, you need to first find it. So you need to find the shock and its properties in your fluid simulations. At the shock, the divergence V will be very, very large, but not really elsewhere. Okay, so you need this there as well. And then there is the diffusion coefficient, which is really a bit of the troublemaker, right? Because that determines the acceleration rate and the spatial transport. There's a natural scale for this that's given by the Lama radius, essentially, but really what you want to know, and even for the Lama radius, you want to know how strong the magnetic field is. And for knowing what the diffusion coefficient really is, you need to know how strong the turbulence actually is. And all this as a function of time and location, of course, because you can be a little bit ahead of the shock, a bit behind of the shock, deep in the interior of the object, and so forth. But in any case, if you look at this equation together with the fluid dynamics and together with something that gives you the large scale and turbulent magnetic field, you can look at the entire object over its entire lifetime. That's what we're going to do. Okay, good. Couple of points to remember as we go into the next parts. So we've seen that our radiation modeling with these objects indicated that the magnetic field has to be very strong. Now, most of that radiation comes from a region in the interior relative to the shock. So anything that happens at the shock or behind the shock that amplifies magnetic field is good enough for the radiation modeling. But it doesn't help at all with particle acceleration, because for particle acceleration, I need stuff ahead of the shock. Because otherwise, my cosmic rays just disappear in nirvana at infinity. So the art really is to drive turbulence ahead of the shock. Now what the turbulence does in a way is the same thing as cosmic rays. It acts with the flow, it evolves internally, maybe there's some damping processes and all these things. So in a way you actually want to set up an equation for this turbulence. Okay, good. And once you have this, what you can really do is you can follow how the turbulence evolves over time as a function of location and couple this non-linearly to your cosmic ray transport equation. The trouble word is nonlinear, of course. To a bit understand the interior evolution of turbulence, I'm showing these two figures because there's a very important process that describes how turbulent wave energy can migrate from some wave number to some other wave number, typically larger wave numbers. And I'm showing a simple example here because this, in a way, at a given wave number is a loss process. I'm looking only at an adiabatic sound wave. And what I'm plotting here is simply, this is density, I believe, variation in density in some artificial units as a function of location. And obviously what you start with is the blue is just a sine wave. So you have a monochromatic sound wave. Great. If you work out a Fourier spectrum for that, the way I set it up, there's a huge peak at a wave number of 1, again arbitrary units. Great. Now you know that perturbations in density travel faster when the density is higher, which means that the crests are a little bit faster than the troughs. So after a while you expect actually something like the red line here. And if you take the Fourier spectrum of the red line there, you see that suddenly there is quite a bit of signal at all the harmonics. I have harmonics here because I have a finite range over which I do the Fourier spectrum. So what you've done is you've taken wave energy from this wave number and distributed this over a range of other wave numbers. This, in the end, is cascading. Now, obviously, if you have electromagnetic turbulence, it can be more complicated than that, but that's the basic idea. So there are some nonlinearities in the wave behavior, and immediately there is transport in k-space. So if you write down an equation for the wave energy density, or differential wave energy density, differential in wave number, maybe it looks something like this one. There's an advective term here. There is a term that describes how the turbulence responds to passage through a shock. It's actually terribly complicated. So this is really a simplification here. And then there is something, a second order term that describes this cascading. And then you have amplification processes with a certain growth rate, gamma g, or damping processes with a certain decay rate, gamma d. So this is sort of an equation of the type you would actually have to solve in parallel to fluid dynamics and to the cosmic ray transport equation. Okay, and since we have so many equations and they're so complicated and we need to always find the shock and we need to have very high resolution, very close to the shock, this time can only be done with spherical symmetry. Okay, now I'll show you a few results for that. So just to remind you, although the code actually has a name, but anyway. So there's the cosmic ray transport equation, there's hydro, and then there is the magnetic field, both the homogeneous part and the turbulent part. And they talk to each other. Okay, so what do I get? So the following plots are a little bit difficult to understand, but I would like to make the point clear, and then we'll see how that goes. So we start on the right panel. What we have on the right are turbulence spectra. Okay? There is a very simplified model for describing interactions with turbulence that mandate that this is all extremely efficient, and the mean free path for scattering is essentially the Lama radius of your particle. And if you do this, then basically you get something like this red line here. Okay, so this is, given the magnetic field you have, no amplification, this is what you get. Now, let's look at what we have here, and we begin with the lines down here, because now we are a little bit ahead of the shock. Some cosmic rays reach their stream relative to the plasma, so they will drive some turbulence. But actually those cosmic rays are few, and the turbulence you drive is relatively little. So you have sort of something like an initial spectrum, and then early on, this dotted or dashed line, this is after 2,000 years, there's a little bit of a hump here, and then it continues. And even that hump later on, after 10,000 years, is largely gone. This means once a cosmic ray gets there, it's sort of 25% of a shock radius ahead, it's basically free to go. The thing is, we have a 3D system, right? So once you go out, the available volume increases very rapidly. So even if you think you have a 50-50 chance of going forward or backward, actually, on average, you're going out. So these particles disappear, which means they will not be accelerated further. Lack of turbulence really limits the maximum energy to which the shock can accelerate. It's really given by the rate of escape to the far upstream. Less turbulence, more escape, lower maximum energy. Now, if you're at the shock, well, there are more cosmic rays, and you've actually significantly enhanced the turbulence spectrum even after 10,000 years here, the solid line, much more so after 2,000 years, where actually, this kind of dotted line exceeds this red one. What does it mean? Well, it actually means you've somewhat amplified the magnetic field, so that the turbulent magnetic field is maybe a little bit stronger than the homogeneous magnetic field you've had. That goes in the right direction for the radiation modeling, but happens only every now and then, really, very early in the evolution. Now, this is a magnetic field, right? There's always depends on the type of wave, there is a corresponding energy density in the kinetic fluctuations, yes. So what does it mean for the particles? So that's what we have on the left here. And now I'm only showing what we have ahead of the shock. Again, this 25% of the shock radius ahead of the shock. So you see that if I had the simplified model, red, basically this, then depending on time, yes, some particles sit there. Typically, this is only high energy particles for the simple reason that the low energy ones don't diffuse so rapidly that the advection prevents them from even getting there. Only the high energy ones do. So the spectrum is some kind of hump here. But if you have the, if you solve this turbulence equation, and the turbulence is not that strong up there, you get many more particles that just sit out there, form some kind of extended halo around the object, and don't do anything else. Maybe they radiate, right? But there's no further acceleration of them. So, again, what does that mean? The weaker the turbulence, the lower the maximum energy to which you can momentarily accelerate. So initially the turbulence is stronger, you reach a higher maximum energy, but later on it becomes weaker. So the maximum energy of particles that are accelerated later in the evolution, after a few thousand years or so, is considerably lower. And this is what you see in the spectrum. And what I'm adding here is, what we're looking at is all particles in the system, inside of the remnant or outside of the remnant in this halo kind of structure. Red again is this extremely simplified turbulence and diffusion model that was in red before on the previous slide. Green is what you get with the turbulence equation. Now you see that if you simply use the ambient magnetic field and have this as your scale for the diffusion coefficient, you basically have to wait for the shock to decelerate. It will do this eventually, but you have to wait for this to reduce the maximum energy. So nothing really much happens between 300 years old and 60,000 years old. Now, if you do this with turbulence, typically your maximum energy is lower anyway because you're not really in this optimal state. But then, over time, the maximum energy goes down. At all times, at the energies to which you can accelerate, you get something like a flat contribution to the spectrum. But at later times, this basically ends somewhere here. Earlier, this ends somewhere here. And then in between, what develops is a convolution of how the maximum energy declines over time and this flattish kind of spectrum. Think of it as a boxcar structure. Okay, and that means, between the initial maximum energy and the late maximum energy, you get something that's softer. Naturally. How soft it is depends a little bit on the details, of course, parameters, but you will get something that's considerably softer. And you see this already after not too long time, I would say. Okay. And now what I'm showing here is simply an animation over time of what the gamma ray spectrum would look like. There's a GeV here, there's a TeV there. Again, the same two radiation components. Blue is pion decay, hadronic interactions. Red is electrons, the Compton interactions. So the Compton spectra are typically hard, at least initially. Later on, as the maximum energy goes down, radiative cooling kicks in, you get spectral modifications, so it actually develops a bit of humps here and generally becomes flatter. And then which one dominates, you see, also depends a bit on time. So the parameters, particularly the gas density in the circumstellar medium that we chose here, make sure that initially this Compton component dominates, but then, after a few 10,000 years, it disappears to a degree, and what's dominating the thing is the hadronic component. Okay, so this all specifically depends on time, and you don't have a situation that one dominates the entire lifetime or the other one dominates an entire lifetime. What you see as well is that the total spectrum somewhere here between a GeV and a few TeV, where we have good data, over quite a bit of the evolutionary lifespan are relatively soft. In particular, if you think that you have conditions in which this blue curve is a bit stronger, for example, because the gas density is higher. This is soft basically all the way. That's actually what we see. I showed initially gamma ray spectra of one particular supernova remnant, which I said is somewhat representative, and that's what you see. Before I go into the core collapse ones, let me make one more remark. When you try to model the cosmic rays you measure directly at Earth, you notice that this works best if you have cosmic ray sources that produce particles that have a spectrum that kind of looks like this dotted line. Right? So this is something that is actually naturally produced if you take a census over the entire lifetime of the object. It's not natural if you only concentrate on the very early phase, when the energy you reach is the highest. Okay, so everything I've shown you up to this point is for type 1As, where you can argue that the circumstellar medium is homogeneous, everything is nice, everything is simple. Reality is different. Many of the supernovae are actually core collapse supernovae, which means there was a massive star. Massive stars produce winds, and these winds produce what is known as a wind bubble. Basically pushes away interstellar medium and creates a cavity. And even worse, these stars go through all kinds of evolutionary phases. So you start with the main sequence, and then depending on the initial mass, there are red supergiants, there are luminous blue variables, there are Wolf-Rayet phases and whatnot. And each of them has a different wind. So one wind drives into the wind material of the earlier state. And this is what we see here. This is a simulation of a very massive star, 60 solar masses initially. Gas dynamics only. But we have wind conditions that mimic an evolutionary track as it's calculated by one of these stellar evolution models. And in the last 150,000 years before this thing is ripe to become a supernova, you see how the bubble, this is density, blue is very low, this kind of light pink or light purple here is a bit higher. How this evolves. The stars spit out these shells, and the shells are done hydrodynamically unstable, so you produce all these protrusions, and then eventually a supernova shock will interact with this, and it's all a mess. It's a mess already in 2D. The mess is worse in 3D. So nevertheless, we try to do this with our spherically symmetric models. This is the best we have. So what you need to do, again, is you need to decide which progenitor star you have, right? And then you compute the wind bubble for it until the star is ready to explode. That depends a bit on the conditions, density of the interstellar medium and so forth, but that's fine, okay? And then you have an explosion, and the nice thing is your supernova outflow will first behave a bit like in the textbook until you hit the termination shock of the last wind phase. What do you get there? Well, part of the shock gets transmitted, part gets reflected, as always with a wave. So what gets reflected moves through already shocked material. So it's probably a weak shock. What goes through starts hitting the next structure, gets reflected there. So in the end, you have a mess of forward-going and backward-going shocks. Okay. Now, if you do this, and it's with spherical symmetry, much of that mess is essentially already eliminated. You get structures like this, and I'm showing this for two progenitor stars. One is relatively low mass, not really, but essentially you have a red supergiant as your last phase. Red supergiants have winds that are so slow that they don't shock, but they push away everything else. The density is very high. You get a little bit of a shell here. The flow speeds are very small. The pressure is very moderate. Temperature, only in the shocked main sequence wind, the temperature is high. Now that's different for this guy here. Initially 60 solar masses. The last phase is a Wolf-Rayet. that pushes everything away, and as that goes through the termination shock, you get extremely hot material, 10 to the 8 Kelvin, over a very large volume. Now, why is this relevant? Well, we're going to run a shock through this. The shock has a certain finite speed, and what happens, and the cosmic ray spectra we get out of this depends on the Mach numbers. If the stuff is very hot, then the sonic Mach number is low. And so I'm showing this here for the massive star, so the one on the right on the previous slide. Shock radius goes out, you have various phases. The shock speed shows all kinds of structures. It basically reflects the structures in the wind bubble when the density varies. And you see that this is the compression ratio. Initially it's about 4. This is like a normal strong hydrodynamic shock, but then later on, basically the entire time the compression ratio is small, and that means soft cosmic ray spectra. Okay, so that means we actually have two effects that shape particle spectra. A, in the wind bubbles, if they're so hot that the compression ratio is low, so this generally makes the spectra soft, at least of particles that were accelerated at these times. And we have this issue that we discussed before, that over time we lose the ability to drive turbulence, and that means our maximum energy goes down because the particles tend to sit a little bit ahead of the shock and not return. And this then makes the global particle spectrum softer. So this is local. This is whatever you can produce at any given point in time at the shock. The other one was global over the entire object. Okay, and then you can work out particle spectra. This is what's being done here. No need to go into detail. I think on the left, what's in brown are actually electrons. Blue is ions, and here I only show the ions. The main point that I want to transport here is that different subpanels is basically different points in time, or the shock sits in different regions of the wind bubble. You see that the spectra change all the time. There is no single spectrum that you get. Okay? And that means, in a way, all objects are different. You would have to understand, what you're really looking at. What was the progenitor star, and so forth. But what you measure locally, of course, is a composite of what all the variety of supernovae in the galaxy have produced. So how do they compare? And here I'm doing this for only 3 initial masses. And I'm showing the spectra you get per supernova remnant from each of them. And you see what actually dominates is a relatively moderate looking, but it's reasonably flat, right? Moderately looking spectrum of the green guy, which is the lowest mass star. And what comes on top is, of those, I expect to have the largest number. Because there's a probability with which you produce stars at a certain mass. It's called the initial mass function, and it declines as the stellar mass goes up. So I have more 20 solar mass stars than 35 solar mass stars, and of those I have more than 60 solar mass stars. All right. So maybe, nature finds a way to simplify all that complexity again in the end. What you've seen is that typically the particle spectra go up to something like 10, 100 TeV or so, but not really higher. There is a structure in the cosmic ray spectrum, it's called the DESY, that sits at a few PeV, and we typically don't get there. Now the question is, do we need other sources like the microquasars that Gustavo talked about last week? Or can we make sort of supernova remnants a bit more efficient, that they reach higher energies? People have looked into this, thought about all kinds of things. none of that really works. You have a chance to do this for very specific fraction of the lifetime, with special circumstances, but not really in general. Okay, so the last thing I want to talk about, this is about iron-16 cosmic rays, but I'm not really talking about this too much because I want to discuss iron-16 cosmic rays. I want to discuss something else, namely how we get away from spherical symmetry. So anyway, there is iron-16 cosmic rays. It's an unstable isotope that's only produced in supernovae. So once you've had a supernova, you have a couple of million years' time to accelerate this iron-60 to become cosmic rays. All right, which means you need one of these guys relatively nearby, because not only do you need to accelerate the stuff, it also needs time to actually get to us. So this is a little bit of a mystery. And we looked into this. The idea is that there is a nearby structure that's probably caused by a number of recent supernovae, and it's called the local bubble. People have tried to model this, for example, Schulreich here, and what they come up with is a structure like this. This is density, temperature, and the iron-60 abundance. Right, so you had previous supernovae that expel iron-60. All these supernovae and the winds of the massive stars have produced this cavity, very low density, very high temperature, and enriched this with iron-60, but actually quite a bit of that is attached to the walls, the compressed ISM here. So if you now look at the next supernova, which in their model would explode there, you notice this is a problem because there is really not spherical symmetry in here. So what we're trying to do is fake 3D. The idea is a supernova outflow is highly supersonic, and that means there is a lot of crosstalk in the radial direction, but the transverse crosstalk is at most with the sound speed, so that's very slow. So if you look at maybe a cone or so, there is relatively little interaction with the neighboring cones, but all the action happens within a cone. And a cone, you can maybe simplify as something that's locally has the same symmetry as overall spherical symmetry. So we can apply our code without changing much to a selection of cones. And we only have to solve for many cones so that you basically cover all regions. And this is what we're doing. So this is essentially a 3D rendering of the same iron-60 abundance on the left that I showed in the 1D profile before. And here you see this projected onto cones. And for each of those cones, you would run our code. And unfortunately, this is not done yet. I was in contact with a postdoc who does the work. But then you can construct a 3D visualization of the entire thing. It's not truly 3D, of course, but you have, in this case, we're working with 48 cones. So it's cheating that a little bit. And in each of these cones, you have one of these profiles for the density. This is just one example of those. Density, temperature, flow speed, iron-60 abundance, and then here, shock radius, shock speed, compression ratio, and so forth. So the same as we had before. Okay, and then you get spectra out of this, not unexpectedly, they have structure. And this is what you can model. Okay, so I was hoping that I could actually show you the result of that really in 3D rendering, but as I said, not yet ready. Good, so let me come to the end. So although shock acceleration in itself is sort of in the textbook described as a scale-free, relatively simple problem, in reality it's highly complex and highly nonlinear. Its efficiency is coupled to the magnetic field in a very strong way. and there is reason to assume that the magnetic field can be amplified, as radiation modeling suggests. But this acceleration is typically efficient only for certain parameter values, or maybe even only for certain parts of the evolution of the objects. Spectra vary. Maximum energy is not as high as one would like. Good, this iron 60 I haven't really talked about. Okay, thank you.
Thank you very much, Martin, for this excellent talk. So let's start with the questions right away. Nice talk, Martin. So I have two questions, if I may. One regards the first part, when you have the solutions for the type 1A. And okay.
I'll try to go there.
It could be, yeah.
That one?
Yes, with regard to the cutoff. Because, okay, we have even, I mean, actually for the core collapse, my question with regard to the cutoff, because there is still this question of, you know, for instance, Tycho supernova remnant, you know that it has this cutoff in TeVs or so,
yes.
And it is still very hard to explain with the pure leptonic or pure hadronic,
yeah,
and then you have
actually that one. That's Tycho.
Okay.
So if you look at the one on the left.
Okay. Yeah. So it's Tycho then. And then you require either to improve the shock model with the, you know, the upstream turbulence to amplify the magnetic fields, and then you can go through this threshold. But also there is the diffusion issues that you discussed, right?
Yes.
So what can really probe this cutoff in supernova remnants is the effective magnetic field amplification, so two-stream instability or mirror instability, as Bell is claiming now, or the diffusion, as you pointed out in the second part of your talk, with this, you know, you do not have the Mach number is not strong enough, depending whether if you have core collapse or, you know, and then you might need some kind of you might need, or to explain the iron, for instance, you need to model better the diffusion, right?
Okay, good. So let's begin with the iron 60. So there was this line in red in the summaries that I didn't talk about. So what you need for the iron 60 really is that last supernova happened 1 million years ago or so, right? So, and we model maybe 100,000 years of that. So, and in the 900,000 years that passed, you need to somewhat hold on to the cosmic rays, or to the iron 60 in particular, right? Because otherwise you can't explain the signal. Now this is for a system in which you've had many massive stars, many supernova explosions, and you might think this is highly turbulent in itself, so you're driving sort of generic turbulence on larger scales, have the usual cascading mirror effect or so. Fine, okay? So this might do it, but here, this guy is really in the middle of nowhere. This is a type 1A, so it's hard to see that this might happen, that you have an unusually high level of turbulence around it.
Right.
So everything, you know, that you want for a small diffusion coefficient, basically, at least upstream, has to be produced by the cosmic rays themselves. And, you know, getting up to kind of this energy is perfectly okay, right? So this rolls over at, well, TeV or so, which means the particle maximum energy at that time will have to be 10 TeV or so.
Right.
Perfectly fine. Easy to get, but you don't get to 1,000 TeV or a PeV.
Right.
Okay. And about the diffusion, because in the cone simulations that you showed,
Right.
you use a model, a diffusion model that was Bohm, Kolmogorov, or
where?
in the diffusion for the cone model, because you
For the cones.
you had
later on.
You assumed the diffusion.
Yeah, but it's basically the same equation here.
Right.
The same turbulence equation. So here we do this as well. The trouble here is technical, that sort of this input simulation that we got for the whole bubble is hydro only and doesn't tell us about the large scale magnetic field. So that means you have to put in some assumptions for that.
Yeah.
And that leads to slightly different evolutionary behavior.
Right, but the diffusion you assume.
Diffusion comes again from this turbulence equation.
Right. Okay. Thanks.
Thanks, Martin. I have two questions. One regarding the spectrum that you showed, the comparison between the bone-like and the turbulent one. What is the spectral index of the turbulence that you're considering here? It's like Krishnan or the Kolmogorov or MHD turbulence?
Okay, so the best answer to that question is this. Look at the black lines on the right. They have no relation to any of those scalings, because really what you're doing here is you're not injecting at large scale and then only have cascading do its thing. You're driving turbulence at a variety of scales. And then cascading comes on top. So at very large K, you always end up with something that's essentially dominated by cascading. And our cascading term basically tends to give you Kolmogorov spectra. Okay? But that's only, the structure of that cascading term.
Okay, thank you. And with regard to the cone simulation, if I understood it correctly, so you divide your 3D system into several cones.
Right.
And in each cone, you have like 1D evolution of the system, considering only the hydro equations in 1D system, right? How does the computational cost of these simulations compare with the full 3D hydro simulation?
Way smaller. I mean, you have to see that the simulation tries to reach better than 10⁻⁶ resolution, spatial resolution for the cosmic rays and for the turbulence at the shock. Okay, that means you need to know the shock and its properties very precisely. If you do this in 3D, you have to worry about the direction of the shock and all these things. This is a mess. Right, so it's not only that the hydro goes from 1D to 3D, it's all the other things also. The mapping would have to be done on the fly. You have on the fly to work out the Jacobians and the differential equations. And well, I could say that this needs a young, energetic person to do, right?
And also the very constraining assumption about the magnetic field, right?
Oh yeah, right. Because then each shock is an MHD shock.
More questions? Okay, I have a question myself regarding the case of the core collapse. I'm wondering how particles get out of such a structure. The spectra that you are computing is actually the spectra that after they escape, or while?
No, so basically all particles stay in the simulation. The simulation extends out to something like 50 times the shock radius.
I see.
Okay, so and typically we end once we've, I can take that one. Once the shock sits in the compressed ISM here and becomes very slow and radiative. This is when we end.
I see.
But the particles are still counted.
Yeah.
That's the advantage. You don't need an assumption for upstream escape.
I see. So is what you get. Is what you get.
Basically included, right, by
Yeah,
your
I see.
driving of turbulence, the diffusion behavior, and so forth.
I see. So I am wondering if you can test directly by, I don't know, one system in interaction with molecular cloud that you can
Okay, then
observe
you
the gamma
again need
rays.
the 3D, right? The molecular cloud will sit on one side. And this is probably so bad that it even destroys the veracity of the smog 3D.
I see.
Because one shock stops immediately, and then the reflected shock will basically move through the entire system to the other side.
Yeah, the way to do this is to get the new environment for your molecular cloud, and then you can consider a shock.
What you can do is a shell around the object. That you can do. That's relatively simple. But I mean, basically, you also have to stop when reflected shocks reach the center, because that breaks symmetry as well.
Yeah, I think that's an interesting case too.
Yeah, right, but not with this model.
I see. Yeah, of course. Okay, more questions? No? We can still discuss with Martin during the coffee break. Thank you very much. Thanks, Martin, again.
Now I will